Hi there, welcome to another lesson in Math 8. Today we're going to be focused on Lesson 9 in Unit 1, Moves in Parallel. The goal of today is to be able to transform lines and to see what happens or what kind of effects transformations have on lines and parallel lines. We're specifically going to visit translation, rotation, and reflection and the effects that happen under a line. Before I do that, I'd just like to remind you of yesterday's lesson or the previous lesson. We talked about rotational patterns. Specifically, we talked about 180-degree rotations when we saw that line segments, they would map themselves when their center of rotation is at the midpoint. When the line or the segment would overlap at some point if the line or if the center of rotation was somewhere else on the line. And then when the center of rotation is not on the line, the segments do not overlap, but the lines end up, the consequences, parallel. Today we're going to see and follow up on those next pieces to it of what happens when I do work with lines that are parallel from the beginning and what happens when I work with other lines that are there. This is kind of a long lesson, so hope you have a comfy seat, and here we go. First part of this assignment is looking for each diagram. We're going to describe a translation, rotation, or reflection that takes line L to line L prime. Then we're going to plot and label points A prime and B prime, which are the images of A and B. The first thing that I want to look at with these two figures, and what I want to make sure of, since we haven't been told that these lines are parallel and they look like they're parallel, is I want to verify that they really are in fact parallel before I make too much of a work. A couple ways that I can do that. First way is I can just take this segment where the line that has AB in it, and I can just take that segment right there. And we can see that that segment has a constant rate of change because it's a straight line. That constant rate of change as we look is rising up 2 units and then running to the right 5 units. I'm going to take that same ratio and I'm going to look at that ratio and see, does my line below have the exact same ratio? And what I've actually noticed before I even got started is I noticed that the distance between B and the line below and A and the line below is 3 units. That's a good indicator that the lines are parallel. To follow up with that, if I just translate straight down, I can see for sure that segment AB does fit right on top of line L prime. And that's a pretty darn good indicator that my lines are parallel. And I think I've actually answered the question for this one to describe a translation, rotation, reflection that takes line L to L prime. If I translate line L down 3 units, I get L prime. And one of the pieces of evidence to that is I notice that segment AB is part of line L, and I maintain that same constant rate of change. So I'm going to go ahead and mark my points right here. This is B prime, and this is A prime. And then my description that I'm going to give for this, I learned from previous video, pencil's not all that great for showing this. We're going to say translate line L 3 units down. You could also say translate line L down 3 units. It doesn't matter with that piece as long as you name the line, name the transformation, and how you are making that transformation happen. Going on to number 2, we see 2 lines that are intersecting, line L and line L prime. What we need to determine with this one is how that happened. I think the easiest way to do that is to recognize that there's just 2 lines, and so the simplest way to do this is just to say that there's been a reflection, or excuse me, a rotation. So then the question comes down to how many degrees of rotation did we actually do here? Well, there's a couple ways to do it. We can put a protractor on it, and we can find out the exact measurement. But the question is, do I have a protractor ready to go? And for a lot of us, we won't have a protractor ready to go. And so what I'm going to do for you today is describe describe this transformation without a protractor. What we'll do with this is we'll look at the pieces that we have. We know there's going to be a rotation. We know it's going to be a certain number of degrees. But since we don't have a protractor, we're going to write this in a different way. I'm going to rotate around point a certain number of degrees. And what we're going to do is we're going to call it, or we see that as we rotate, figure AB or segment AB maps to L prime. So we know now that that's my rotation. So what I'm going to say is let there be a rotation of line L around center A d degrees. Now, since I'm saying d degrees, I don't know exactly how many degrees, which means I haven't told anybody how I can stop the rotation. And so I need to be able to tell somebody when to stop rotating. Normally our degrees tells us that, but since I don't have that, I'm going to have to do a little bit more. I do need to add in my direction, and for this one I'm going clockwise, d degrees clockwise. And I'm going to use one major word here, until. That is how long it's going to go on. Until line L maps or snaps to line L prime. For the degree sake on this, I could use a protractor, but the likelihood of me having a protractor right now is going to be pretty low. And I know for a lot of us, it's going to be pretty low. And so I just want to make sure that we know exactly how to write a description when I don't have a protractor and when I want to be accurate so that a person knows how far to rotate and when to stop. So again, name the rotation, name the figure, name the center, how many degrees, and if you don't have the exact degrees, tell when to stop. Hopefully that makes sense to you. Moving on to the next piece, we're going to talk about now parallel lines. When I take parallel lines and I use parallel lines, we're going to see some effects that happen here. So we're going to use a piece of tracing paper again. If you don't have any tracing paper with you right now, please pause the video and go and find a blank sheet of paper that you can use for tracing video or tracing purposes. Moving on to this problem, use a piece of tracing paper to trace lines A and B and point K. Then use that tracing paper to draw the images of the lines under the 3 different transformations listed. As you perform each transformation, think about the question, what is the image of 2 parallel lines under a rigid transformation? This right here is going to be a very key thing for everything that we do. We're going to come back and answer that question after we've completed these 3 rigid transformations. So here we go. Number 1, let's go ahead and use, let's reuse something here. We're going to put this one as point K, and then I'm just going to include lines A and B. So we're going to just use a part of our paper here, because we know that lines technically go on forever. And we're going to use point K as our center of rotation, as it said. And this one here is line A, this one's line B. The first thing we're supposed to do is translate lines A and B 3 units up and 2 units to the right. So we don't really need line K at this, or point K at this point, but it will help us as we look at our translation. 3 units up and 2 units right. Oh, darn, point K is going to go off the page. So let's pick another point to work off of. Let's go back in our line, and we see there's a nice little point there. There's a nice little point there. The idea is that we need to find a nice point that I can go ahead and calculate my rate of change all the way along as we go. So I'm going to go ahead and use this point right here. And as we do this, we're going to change our lines. We're going to rise 1, 2, 3, and then run 1, 2. What do you notice about the changes that occur in lines A and B after the translation? Well, pause the video for a second and look. What observations did you have? As I look at this, my lines, they really didn't change. I mean, I still see parallel lines. A and B still appear to be parallel. And it says, what is the same in the original and the image? Well, the lines remain parallel no matter what I did. I mean, this translation, they moved to a new position, but what I notice is that lines are still parallel, but in a new position. This next question in some ways kind of seemed a little redundant to me. What is the same in the original and the image? Parallel lines. Okay. Problem number 2 says we're going to rotate lines A and B counterclockwise 180 degrees using K as the center of rotation. Now, as you recall, when we did a 180 degree rotation around a point on the line, there was something that was happening with this. When we look at our last lesson and we do 180 degrees, the image of the segment overlaps with the segment and lies on the same line if the center of rotation is a point on the segment. So as we look at this and we see that point K is on the line, that should indicate to us that line B should stay in its exact same place when we rotate 180 degrees. So let's see what happens. Remember, 180 degrees is half of a circle. We're going counterclockwise. I'm going to rotate. There's approximately 90 degrees. We're going to continue around until, look at that, the figure, or line B, rotates 180 degrees around K. Point K is on line B, and when I rotate line B 180 degrees, line B overlaps on itself. It says, what do you notice about the changes that occur in lines A and B after the rotation? Well, it looks like line A and B just turned around, right? Line B is still the same, but line A is in a different position. Changes that occur to lines A and B after the rotation. Well, we see that line A is in a new position. Right? That's about the only change that really happened. Well, and A and B look backwards, I guess. It's kind of how I see it when I look at those ones. Line A is now below line B. But it says, what is the same in the original and the images? Well, line B is in the same spot, same position. And I think the bigger thing is the lines are still parallel. Hope you're going to catch on to a common theme here. We're going to reflect lines A and B across line H. Okay, so now we're going to reflect over a different line here. So what we need to do with this to be able to make sure that we get a nice reflection, so when we reflect, our figures move together, but they maintain the same distance away from line H. So what I'm going to do is just go ahead and mark a little mark right here. And all that is to, you notice that I'm making this mark 90 degrees, and I'm going to go ahead and put the same mark when I draw this. I'm going to put another one right here. And all those are little marks to help me line up for when I make my reflection, so that I reflect across the line and I take my figure AB, my two lines, and I get them exactly where they need to be on their reflection. This helps me to keep a perpendicular relationship to the line of reflection the way that it's supposed to. So we're really going to pay attention to K. And if I do this right, a 90-degree reflection, or 90 degrees from that, should end up coming up. That little line that I just sketched in there, it should end up going in that exact same spot, just on the opposite side, pointing right at K. Here we go. And there we go. To be able to graph these two lines, I want to be able to find a couple of nice happy points in here. There's one right here. And then I need to be able to come down. There's one right there. So that'll be A. Then we see B. Looks like it'll go through right there. I think what's really interesting about this is I actually just noticed something that I didn't notice at the very beginning. I'll tell you about that here in a second. So first off, there's line A. Whoops, I'll double check to make sure I'm getting the right line before I label it. That looks like line B is closer to line H, so this should be line B prime, and this one should be A prime. And what we should see with that, with our line, let's go ahead and put K in there because, whoops, let's line these little marks back up. Let's put point K back in here. And there's a little tiny bit of a difference with where point K is because, only because, where the lines sit. But what I noticed was this. As I was drawing these, I noticed that line A and B have a vertical distance of 1 unit away from them. And I see the same thing up here above in my other drawing. That's kind of cool because then that helps to verify to me that these lines continue to be parallel no matter what I do with them. So what I noticed about the changes that occur in line A and B, well, they seem to have switched positions under the reflection. So we see that now B is above A, where in the beginning it was A on top, B on bottom. Now it's B on top and A on bottom. But the same as the original is parallel lines. The big idea here when we're talking about this question right here, what is the image of two parallel lines under a rigid transformation? You guessed it. It's still parallel lines. That relationship is so strong that it will never change under a rotation, a translation, or a reflection. These lines will continue to be parallel no matter how we manipulate them under a rigid transformation. That's our major concept of transforming parallel lines. So let's take a look, a little bit of a challenge. It says when you rotate two parallel lines, sometimes the two original lines intersect their images and form a quadrilateral. What is the most specific thing you can say about this quadrilateral? Can it be square? A rhombus? A rectangle that isn't square? Explain your reasoning. When I look at this specific image right here, when I'm rotating two parallel lines, and we have to ask the question, it says, what is the most specific thing you can say about this quadrilateral? Well, I think the most specific thing, knowing what we know, when they told us that these lines are parallel, sometimes you may have seen little marks on lines that look like this. And then on another set of parallel lines, you would see this. Well, these marks are called congruence marks. In this case, this means that these two lines are related and they're parallel. And these two, since they have two little carets on them, are parallel. But this set of lines and this set of lines are not parallel because they have different numbers of carets on them. Knowing that information, that tells me that this side and this side is parallel, and this side and this side is parallel to each other. Under those characteristics, when we have a figure that has two sets of sides that are parallel, we have either a parallelogram or a rhombus. But it is not a square or a rectangle in this case, because there are no 90-degree angles. That's our big piece with it, but I can for certain say that this is a parallelogram or a rhombus because I have two pairs of sides that are parallel to each other. All right, a little bit more. If you need to, go ahead and pause the video, take a break, come right back, and finish up the lesson with me. We're actually going to go ahead and do some 180-degree movements here. The diagram shows a line with the points labeled A, C, D, and B. And on the diagram, we're going to draw the image of the lines of points A, C, and B after the line has been rotated 180 degrees around point D. Label the images of the points A prime, B prime, and C prime. And then we're going to say, what is the order of all 7 points? Explain your reasoning, or explain or show your reasoning. Going back to what we talked about again in lesson 8, under 180 degree rotations, we see that our center of rotation, D, is on the line, or is on, and in the previous lesson we saw it's on the segment. But when we see that we have the point on the line, when the center of rotation is a point on the segment, we should see that the segment overlaps with the segment and lies on the same line. Using that information is going to help us as we rotate our image here. We're going to use center D, we have B, we have C, we have A, and we have the line that we're going to rotate around center D. 180 degree rotation. Remember, comes and rotates. We know that since the point is on the line, we're going to end up overlapping on the line. And I hope you notice a relationship as we look at these. Let's go ahead and mark. We're going to do point B, point C, and point A. I'm going to put this right here so I have some reference for me for where these are. This one was B prime. This one right here is C prime, and this one here is A prime. I think what's kind of cool about this is I look, if you remember the example that I showed in class, and obviously if you haven't been in class, I want you to think about a sprinkler that's on the big farms here in Moses Lake, the big circles. And as you look at that circle, if you look at it overhead, you'll see that sprinkler, as it turns around its center post, its center point, that the distance from that center never ever changes. I think we can think about the same thing here. It actually appears that point D, we see point B prime and B, they have the exact same distance away from the center. And C prime and C have the same distance from center D, and A prime have the same distance from center D. So what are all 7 points in order? Explain or show your reasoning. Well, I'm going to talk about my graph here, and I'm going to say, as you can see in my graph, the order is A, C, B prime, D, B, C prime, and A prime. And the reason for that, what we call this kind of is like a palindrome, where something is the same order forward and backwards. The only difference is I have primes. The reason for that is because of that 180 degree rotation, where the center of rotation was on the line, and so when I rotate my image, I should see all of the points back on the line because my line is going to overlap the exact same line. Okay, moving on. The diagram shows a line with points A and C on the line and segment AD where D is not on the line. What was our consequence of the center of rotation not being on the line under a 180 degree rotation? Again, remembering back to our notes, when the center of rotation is not on the segment and we have a rotation of 180 degrees, we are going to see that the image of the segment does not overlap with the segment, and we learned that those two segments should be parallel underneath that rotation. So as we watch this, we want to be very careful to look for that relationship, recognizing that this line containing the points A and C will not be on itself because we're rotating off a point that's not on the segment, but we should see another line that becomes parallel to this line. Not this line, but parallel to this line. We'll also see another interesting relationship as we do this. So taking our segments and taking our lines, let's see here. Rotate the figure 180 degrees about point C. Label the image of A as A prime and the image of D as D prime. So I guess I need both of these on here. And we're going to have D right here A right here, and we're going to take this little segment right here, and then I'm going to put point C on here too, because this is going to help me to line this up. Point C. 180 degrees means that this part of the line, this segment right here, should rotate, since point C is, let's see here. Oh, whoops, I misled you. I'm sorry. Since point C is a part of the line, and I'm going to rotate 180 degrees around point C, that means that AC should end up back on this same line. Here we go. Okay, there it is. So we're supposed to label the images of A prime and D prime. So here's where D is. And whoops. Let's put A on there as well. And then let's go ahead and use a straight edge. This one here is A prime. We know it has to be A prime because it's on the line. D was not on the line. And there's two lines there, two segments. It says, what do you know about the relationships between angle CAD, so here, angle CAD, and the relationship between angle CA prime D prime? Explain or show your reasoning. Well, let's go back to that rotation, and we look and we see that what I actually drew was just the angle of CAD, and then we rotated that angle all the way around. Now, I want you to look at the picture on this. What do you notice about the angle? Is it changing its measurement? Is it getting larger or smaller in its measurement or in its opening? And if you're thinking, well, this is a rigid transformation, that can't happen, you're thinking exactly what we need to have. Under rigid transformation of rotation, angle measures are preserved. So we would say, what do you notice about the relationship between the angles? I noticed that angle CAD and angle CA prime D prime, we're going to say measure, so M, measure of angle and measure of angle are equal. Rigid transformation preserves or keeps the same, preserves angle measures. Now that's a good description for any time that we ever do a rigid transformation if we have to describe the length of a segment or the measure of an angle. All right, one more before we go to our summary. The diagram shows two lines, L and M, that intersect at point O, with point A on line L and point D on line M. Rotate the figure 180 degrees around O. Label the image of A as A prime and the image of D as D prime. Show what you know about the relationship between the angles in the figure. Explain or show your reasoning. I'm going to grab a new piece of patty paper here because I've used that one up quite a bit. We're going to go ahead and trace on here first angle OAD, and then we'll rotate that 180 degrees around center O. We're going to see that same type of relationship since we're working on these lines. We're going to be rotating two lines at the same time, but those two lines at the same time have points on them. And we remember that when we rotate 180 degrees on a line, if the center of rotation is on the line, then we should see those lines overlap right back to each other. In this case, center O is on both of these lines at that intersection. So 180 degree rotation should take A back to line L and D back to line M. Here we go, 180 degrees. We see that we get to segment D gets right here, but that's not a 180 degree angle because I don't see D straight in a straight line across from itself. I continue to rotate further around until D maps back to M and A maps back to L. And what's interesting is they map back at the exact same time. Well, think about that for a minute. Why would they do that? Pause the video and think about that. And now that you've come back to me, I want you to go ahead and mark these. Make sure they're marked on there. Let's get them drawn on. We see A prime here, D prime here. Now we think about this. When we rotated from here to here, we got a certain number of degrees. We're going to call that D degrees. How many degrees was that of rotation from here to here? Well, if the lines came back together at the same point and A prime and D prime matched up at the same point, then that would tell us that this right here is also the exact same D degrees. So what do you know about the relationship? In this case, it says, what do you know about the relationship instead of what do you notice? What I know about the relationship between two angles in this figure is that these two angles must be equal to each other. And what do I know about the angles? The angles must be equal because rotation preserves angle measures. Same thing with all other rigid motions. They preserve the angle measures. One other thing for a quick throwback here for you to 7th grade math. The 7th graders that haven't gotten to this yet, this is an introduction to it. When I see two angles that share a common vertex and they're across from each other across that vertex and they have the exact same measurement, the relationship that we call here is vertical angles. Hopefully that's something that sparks memory, but vertical angles are always congruent. And why are they always congruent? Well, because under a 180-degree rotation, we see that the original angle compared to its image is going to have the exact same measurement because of basic rigid motion. Alrighty, we're almost there. Let's recap everything now. Rigid transformations have the following properties. A rigid transformation of a line is still a line. A rigid transformation of two parallel lines results in two parallel lines that are the same distance apart as the original two lines, right? So we go rigid transformation, a line is a line. Rigid transformation of two parallel lines results in two parallel lines, same distance apart. And sometimes a rigid motion takes a line to itself. For example, what we saw right here, and we know that because when the center of rotation is on the line itself under a 180-degree rotation, we would see this right here, 180 degrees only. When we talk about sometimes, that sometimes is only a 180-degree rotation. We know a couple other things. A translation of a parallel line. The arrow shows a translation of line M that would take M to itself. So if you take this line right here, line M, and you simply, let's call this one line M right here, and you simply just translate that line, it remains on the line. It will take M to M. A rotation of 180 degrees around any point on that line will be line M. Again, it will just take the distance, such as B to B prime. It will take it to the opposite side of the center of rotation and still have the same distance away from that center. A reflection across any line perpendicular to the line is the third point that we want to have here. A reflection of line M across dashed line M will just be itself. So as if I were to fold this line straight over here, cross this line, or fold this figure across this line, line M would just land right on top of itself. As we can see, basic rigid transformations always maintain the same shape and the same size. Even when we start using different figures and we start talking about lines and parallel lines, we see that the exploration that we made under 180 degrees in lesson 8 has the same effects and the same consequences. We see that the consequence of rotation around a center point maintains distance from that center point for all points and their images. I hope that everything is coming tied up nice and pretty together. You're doing such a great job with this work. I'm really proud of you. I'm really excited for the work that you're doing, and we're going to continue to get better and better at what we do. I just thought of one lesson that I've always taught, and that says look at the back side of the paper before you move on. So I'm just going to look, and it's a good thing I did because there's a little more to lesson 9 that I was about to miss. So these facts that we have make an important conclusion. I'm gonna highlight that one. An important conclusion. If two lines intersect at a point, we'll call that point O right here. So I'm going to go ahead and just label that O because they said so. Then a 180-degree rotation with the lines at center O show that vertical angles. Oh my goodness, there's that word that I brought up. Vertical angles are congruent. This angle here is vertical to this angle here. And the reason for that is because of the rigid transformation of a rotation of 180 degrees around a center. Rotating both lines by 180 degrees around a single center that's common to both lines will produce two angles that are exactly the same. So here's our introduction glossary term to vertical angles. I'm really excited to continue on with this geometry. This is the end of the lesson today. Don't you dare give up, and I'll see you for some more in the next video.